And now, Storm Team Weather with meteorologist Mo Shamel.
Hello, I'm meteorologist Mo Shamel. You've probably seen me on Good Morning West Tennessee as you were getting ready for school in the morning. Well, turns out today we're going to do a little bit of a tour of a station, and we're going to get you a little knowledge on how things work here in the weather department and how we go about day by day here. But first, we're going to take a look at first of all, our setup here. First of all, this is my station here at WBBJ 7 Eyewitness News. This is my weather station. This is what we call WSR. This is the weather company MAX system. This is where I put the forecast together day in and day out here, and today we're going to talk about some of the tools that we use on a day-to-day basis here at the station. But again, we put the forecast together here. This is a multiple computers. We've got two of them specifically that we use to tell the weather, and then also others that are constantly monitoring for like severe thunderstorm watches and warnings that are then displayed on TV to show you those things. But one of my main tools that I use day in and day out is what we call a chroma key, and that of course is the green screen as it is sometimes called here. This is a look at that setup here. This is our chroma key wall. This is where I stand most of the morning here for us as I do forecasts day in and day out for you here at the studio. First of all, we're going to talk about some of the tools that I use day in and day out. And first of all, one was useful this morning, tracking rain across portions of West Tennessee. So how do we do that? How does radar work? That is WSR 88D. That is called a Weather Service radar, and that is we've got hundreds and hundreds of those across the entire country. But how does it work exactly? Well, it turns out we've got an antenna that's within what we call the golf ball, and that antenna is rotating constantly, and it is sending out a signal that's going out. That signal is roughly 175,000 watts that goes out into the atmosphere. It turns out as it goes out, though, it turns out the Earth is round, so that beam actually starts to go and climbs in elevation, so it is limited. And so the further out that beam goes, the more useless the data becomes, because sometimes we just can't see what's going on closer to the surface. And that's why we have spotters that are out looking at different elements and reporting to us what they're actually seeing versus what the radar is seeing. But the radar itself is actually only scanning about 10% of the time. The other 90% of the time, the radar is actually listening for those echoes. So what happens is the beam goes out, and when it runs into something, it sends back an echo to the radar. The radar then interprets that echo, and that's what we see as that radar data on the screen. In fact, you might be familiar with this scene here. This is what we call Storm Tracker 7 Max radar. Here's the golf ball, and typically this is typically spinning. You can see the beam coming around here. It's going around and basically sending pulses out in every single direction in 360 degree directions. And again, once it hits a beam, hits something, it returns that signal, and then we get to interpret that as a radar return. And this is what that would look like. For example, there might be a few sprinkles at the time of recording this. There might be a few sprinkles going on up there. This is Benton County. This is Camden. And then this is Huntington there and Wildersville. And again, these are some of those returns that the radar is actually seeing. So it's sending the beam out, and then when it sees something, it sends that beam back to the computers, and then we get that interpretation. But remember, the farther away we get from each of these radar sites, the higher the beam is in the atmosphere. So that means sometimes it's missing what's really going on down at the surface, and that's when it gets a little critical with severe weather, and that's why we have to have those storm spotters and folks that are on the ground that are also sort of giving us what we call the ground truth. Now, where we do have a lot more rain on one of these radar sites, this one's actually over in Nashville right now, and we've got, again, a lot more rain here in this particular scene, where we've got a cold front that we had moved through earlier this morning, and that's going to continue to work its way to the east there, but that's where we do have quite a bit more rain, but I thought I'd use that to give an idea. Now, when we start to put all of these different radar sites together, that's when we get what we call a mosaic, and that basically gives us a much better idea of what's going on over large entire areas, and we'll get a good glimpse of one of those tools here coming up in just a second. But first of all, how do we get this data in the first place? So how do we know the temperature, the dew point, the wind direction, the pressure, all these things, whether or not the rain is plain old rain or freezing rain? Well, we have what we call ASOS stations, or this is called ASOS data collection. That stands for Automated Surface Observation Systems. And of course, these are typically at airports. One of the main ones here in West Tennessee is located over at what we call McKellar Sites Regional Airport. That's one of our primary measuring sites. So it is, again, measuring temperature and dew points. It's measuring our precipitation type. It's measuring how much rain or precipitation is actually falling in that particular location. And then we also have what's called a laser ceilometer. And this is a laser beam that's literally being pointed up to the sky, but it's measuring where we have different layers of clouds, which is important at the airport, well, it turns out, because, well, we have planes that are taking off, and they got to know where the ceiling is and where they have to use their eyes versus instrumentation in order to keep you safe while the plane is flying. So this is all important stuff that happens. So here's a scene that I use day in and day out. This is a live look out the window in downtown Jackson, of course, and there's a particular part of that scene that I use every single day. Remember that ASOS system? All this data that you see here comes from those measuring stations. So 67 degrees, we know it was 67 degrees at the time of this recording. The dew point was about 58 degrees. And then doing some math here, we get a 73% relative humidity, and the winds are currently out of the northwest at about 3 miles an hour. And the barometric pressure, of course, whether it's rising or falling, tells us whether our proximity to a different pressure setup. 29.76 inches specifically was the pressure at the time of this recording. But we know what's going on at the surface, but what about the rest of the atmosphere? It turns out the atmosphere is 3 dimensions, right? We got to know what the temperature's doing as you go up in the atmosphere, because that tells us whether the atmosphere has energy, whether there's shear involved. All these things directly affect the thunderstorm's behavior. And one way we get those measurements are released at National Weather Service stations across the country here, one of which is in Memphis, and they release what are called weather balloons. They have connected to it what's called a radiosonde, and this radiosonde measures the temperature as it goes up. This is what that data looks like. This is going to be a complicated look here. Actually, in fact, I'm going to go back over to our screen to actually kind of show you some of this data here to give you an idea how that ultimately works. Again, we've got the red line, which is actually temperature, the temperature line tells us where the temperature is going. The green line is actually telling us the dew point. It tells us the change, and the dew point will actually indicate basically to indicate where the dry air is in the atmosphere, of course. And these lines that you see here are actually they're weather flags. It tells us how high the winds are and what direction they're blowing. Notice it changes as you're going up in the atmosphere, and that's important, especially when we're forecasting severe weather. We got one of the main elements of for severe weather is what we call veering with height. So that means the wind direction is actually changing as you're going up in the atmosphere. And of course, that's what leads to severe thunderstorms. But there's another tool we use every day, and that is to look at clouds. How do we look at clouds? Well, the main system we use is called GOES. That stands for Geostationary Operational Environmental Satellites, R. And of course, we've had 4 of these launched. And basically, it's a camera, a really glorified camera that's essentially rotating around Earth, and it is always looking at the clouds at all times. But it turns out there's some benefits and detractors for that as well. This is roughly what a satellite would look like. I'll step out the screen so you get an idea of what one of those satellites might actually look like as it's rotating around Earth. But this is what it sees. This is what we call visible satellite. That means it looks at exactly what's there. And we've got a lot of cloud cover across the country. You can see the huge mid-latitude cyclone here across the country. The disadvantage about visible satellite is it's visible. So that means when the Earth is turned around the other direction, we don't have sunlight, so you can't see that. So the camera can't see that. So a visible satellite's not useful when it's nighttime. However, during the night, we are able to see clouds by using a different perspective, and that's called infrared. If we take a look at the temperature of those clouds, the colder they are, the stronger the storms, or the more likely it is it's producing some kind of precipitation. So we get brighter colors here, even when we use what we call infrared satellite as a result of that. With another perspective we can look at is called the water vapor, measuring how much moisture is in the atmosphere. This water vapor satellite gives us that. So we got a lot of dry air punching across the central part of the country towards the Great Lakes region, while a cold front's moving to the east, but we got a lot of moisture and heavy rain and thunderstorm activity down here to the southeast of the cold front. So this is what we call water vapor satellite. Another advantage that we have, you can see just how much moisture is pushing northward into portions of Alabama and western portions of Georgia. when we superimpose radar to that, of course, this is looking at what we call the mosaic. So it's looking at multiple different radars all being put together in one large picture. And this is when we get what you're typically used to seeing, and that's radar. This is something that we certainly use every single day there as well. So again, that's how we get our warnings and watches and warnings and whatnot out for you. But again, this is a cold front, which basically it denotes the leading edge of colder air as it pushes eastward across the region. And of course, these areas of low pressure and high pressure basically tell us where the weather ultimately will occur, essentially. To wrap up here, I'll just go ahead and kind of explain my job here as a meteorologist. My job is to interpret all that data, of course, and that is to basically give you the most accurate forecast at the end of the day. It is a guess at the end of the day. But again, if you're interested in getting into weather, one thing I would suggest right off the bat is math. Get real good at that. Be a big fan of math, and physics, of course, is a big part of this as well. I don't use it day to day, of course, but I do need to understand how the weather, the atmosphere behaves and works, and that's how I ultimately determine what I think the weather ultimately will do for us day in and day out.